To truly master a quantum mindset, we have to move beyond metaphors and look at the actual mechanics of how the universe processes information. For an engineer or a strategist, this means transitioning from the Clockwork Universe of Isaac Newton to the wave function universe of Erwin Schrödinger. In a classical system, we assume that every object has a definite state at all times. This is the foundation of Boolean logic. A switch is either on or off, a bit is either 0 or 1. This works perfectly for building a toaster, but it fails when you are building an autonomous swarm of drones or a global financial network. In these high-complexity environments, the state of the system is often unknown until it is tested. In classical engineering, your logic space is a line between 2 points. In a quantum mindset, your logic space is a sphere. This is modeled by the Bloch sphere, a geometric representation of a qubit. While a classical bit can only be at the North Pole 0 or the South Pole 1, a quantum mindset allows you to operate anywhere on the surface or even inside the sphere. This represents superposition in a way that is functional, not just theoretical. It means that during the design phase, you aren't just choosing between option A and option B. You are maintaining a state that is a linear combination of both. In practical terms, this means architectural agility. You design a system that hasn't decided what it needs to be yet, allowing the environment to provide the final input that collapses the design into its most efficient form. One of the most profound shifts is moving from modular thinking to entangled thinking. In classical DevOps or systems engineering, we try to decouple everything. We want microservice A to be completely independent of microservice B. But in the real world, systems are entangled. Quantum entanglement means that two particles are linked such that the state of one instantly influences the state of the other, regardless of distance. In a complex engineering environment, your security protocols are entangled with your latency, which is entangled with your user experience. If you change a dead piece of code in one area, you might cause a spontaneous collapse in an entirely unrelated sector. A quantum mindset recognizes these invisible threads. You stop looking for linear causality, a cause B, and start looking for non-local correlations. You treat the entire system as a single unified wave function where everything is breathing together. Classical logic treats noise or conflict as something to be eliminated. If two engineers have different ideas or two signals cross, we see it as an error. A quantum mindset sees this as interference. In a wave system, when two waves meet, they don't just crash, they combine. If they are in phase, they experience constructive interference, doubling the strength of the signal. If they are out of phase, they experience destructive interference, canceling each other out to 0. A quantum literate leader uses this to solve problems. Instead of trying to outshout a problem, you introduce a counter signal. If a project is heading toward a catastrophic failure, a high-energy peak, you don't hit it with a wall of force. You introduce a phase-shifted intervention that causes the energy of the crisis to destructively interfere with itself. You solve the problem by making it zero out. Perhaps the most challenging part of this mindset is acknowledging the measurement problem. In quantum mechanics, the act of observing a system changes the system. This is a fundamental truth in engineering and leadership. The moment you put a metric on a team, an observation, the team changes its behavior to satisfy that metric, often losing the quantum potential they had before they were measured. A quantum mindset understands that absolute monitoring is a myth. The more precisely you measure the position of a project exactly where it is right now, the less you know about its momentum, where it is going. This is the Heisenberg uncertainty principle applied to human systems. To be a quantum engineer, you must learn to monitor a system lightly. You gather enough data to understand the probability cloud without forcing the system to collapse into a rigid, underperforming state. Finally, we have the concept of coherence. In a quantum computer, qubits are only useful if they stay coherent, working together in a synchronized wave. The moment they lose that synchronization, decoherence, the computer becomes just a pile of expensive junk. In the next decade, the most successful organizations will be those that maintain phase coherence. This isn't just alignment. It's the ability for every member of a team and every component of a hardware system to vibrate at the same frequency. When a system is coherent, it can perform calculations and actions that are exponentially more powerful than the sum of its parts.